Hi. We we were examining MSI combinational circuits. The last element among these is the comparator. Comparator compares two 4-bit numbers. So if I draw it as a box, so it's like that. Assume that there is a box. What is inside is this circuit. So what this circuit does, there is a 4-bit A number and another 4-bit B number, and we say A bigger than B, A smaller than B, or A equal to B. So three outputs, output variables, and there are 8 input variables here. So if you draw a truth table, it's going to be like that. A0 up to B0, total 8 inputs, and F1, F2, F3, 3 output functions. So if you draw a truth table like that, since we've got 8 independent variables here, 2 to the power 8, 256 lines that we are going to have in this truth table. So if you do the classical analysis, then you're going to find these 3 functions, minimal functions, and design these meaningful functions. In order to find the minimal function of those 3 functions, which has 3 independent variables, not easy to find. It takes quite a long time. But it is possible, of course. In these cases, we already said that if the size of the functions that you're going to realize increases, you've got to use the modular circuits first. We have done it in parallel adder circuits. So we considered 2 bits addition first, and then we expand this model by adding these models to each other. You can get a bigger size circuit. We will be doing the similar thing here, saying that how we can say that 2 numbers, they are equal. So in this case, we are going to compare 2 numbers, A and B. Only 1 bit has got. So this number bits could be both of them 0, one of them 0, the other 1, 1. It could be one of those, isn't it, when you compare them. So you can easily that these two, if the value of these A and B elements are 0, 0 or 1, 1, they are equal. So in this case, you can say that A equal B. So in this case, you're going to say A is smaller than B. And in this case, you're going to say that A is bigger than B. So let's start from that equal case. We are going to introduce a new variable which is called xi and define like that. So if you look at this function, if both of the bits are the same and they are equal to 1, so this term becomes 1. If both of them 0, that's case, prime of those gives you 1, 1, and this becomes 1. So when the equal numbers values are 0 equal or 1 equal, this new variable that we defined is going to be 1, isn't it? So you can say that when xi is 1, then these 2 bits, they are equal. That information tells me, in order to say that 2 4-bit numbers equal to each other, each bits of these A and B numbers must be the same. So you can write this A equal B function directly by using this x new variable. Here you are. x0 means a0 is equal to b0. x1 is equal to 1 means a1 equal to b1. x2 equal to 0 means a2 is equal to b2. x3 equal to 1 means a3 is equal to b3. So if they are all ones, that means a equal to b. So how we can, so this you can represent this as this is exclusive NOR function. I can tell it how it becomes like that. AI XOR BI is equal AI prime BI plus AI itself BI prime. This is exclusive OR. To make it this, you're going to get the negation of it. In other words, this is XI BI exclusive OR prime of it, isn't it? So it is just one gate, you see. So 1, 2, 3, 4 exclusive OR gates. Gates output connected to AND gate gives you that, isn't it? So here you are. That is this one. x0, x1, x2, x3 comes to the input and this AND gate, and the output is this. So that is this function. Okay. Now we are going to see that we could use this x new variable in order to determine the other functions. How we could do it? We can say in general that while we are comparing two numbers, the most significant, we can compare the most significant bits first. For example, let's say A and B. Let's say A3 is 1 and B3 is 0, whatever the others are. If A3 is 1 and B3 is 0, you can easily say that without looking at the other bits values, A3 is A is bigger than B, just by looking at the most significant bits. Why is that? Because the highest number that you can get, when this is 1, the smaller number that you can get here is 2 to the power n, or in this case 2 to the power 3, isn't it? 4 bits, 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, so this is 8, isn't it? The smallest number that you can write, of which most significant bit is 1. The highest number that you can write, of which most significant bit equal to 0, is 7. So you can put 1, 1, 1 here, and that is 7. That 7 is, in general, 2 to the power n minus 1, or 2 to the power 3 minus 1. So you can easily say that A is bigger than B if the most significant of A is 1 and most significant of B is 0. So in this case, you don't have to look at the other bits. Now I am writing now directly A bigger than B function. This is C2. In Turkish that is çıkış. That's why çıkıştı. So the first bit, the first term here is A3, B3 prime is the product term corresponding to this, isn't it? This becomes 1 when A3 is 1, B3 is equal to 0. If this is the case, so that these are the most significant bits, then my function becomes 1 without looking at the others. Now we can consider one bit further. One bit further, saying that if the most significant bits are the same, So that means here we said most significant bit of A3 is bigger than B3. Now we're going to say the opposite. Not the opposite. Say that if they are equal. If they are equal, then that means x3 is equal to 1, isn't it? In this case, I am going to use the next bits. That means next bit, this bits I'm going to compare. If that is 1 and that is 0. So that means most significant bits are the same. A2 bit is 1, B2 bit is 0. So that's going to be 1. When the most significant bits are the same, I am going to use this term now to say that A is bigger than B. So that is the alternative case for A bigger than B. If the two bits are the same, then we are going to compare the third bits. If the third bits of A is 1, which is A1, and third bit of B, which is B1, is 0, then when first two bits are the same, that's going to be 1. That is the third case. And this is the fourth case. That means first three bits are the same. The last bit for A0 is 1, B0 is 0. That's going to be 1, and that means A bigger than B. So there are four alternatives. When you add them up, you're going to get the function. So this function here can be realized. How am I going to realize it? The reason I divided this operation here, as you see, as this operation. Why is that? I'll explain to you now. That's the x3, b3 prime. Here that is a3 prime, b3. You see, we need to use these multiplications here. A3 prime, b3 prime, a2 prime, a1, b1 prime. So these four here is the output of these AND gates. So the output of these AND gates, here you are, x. So that is this, isn't it? So the second one here, if you look at here now, that is x3, and that is now a2 b2 prime. So this is a2 b2 prime multiplied with x3. So this is this term. So I can show it to you in different color. So this is this one. And this one is this one. The third one. And the fourth one is this one here. When you add them up, A is bigger than B, you can say that. What we have done is this, what we have done here is this. We could directly write these as one XNOR gate. I didn't write it like that. I made this here. So for example, these X values are, you can get these X values by using just one XNOR gate, I said, but I didn't realize it by one XNOR gate. I realized it like that. Why is that? Because I need these values here. These are the things that I need for the other functions. That's why I divided it like that. So I'm going to leave the third function to you. While we are saying A is bigger than B, we compare the most significant bits. If A most significant bit is bigger than B, I said. Now we are going to say the opposite. If A significant bit is 0 and B significant bit is 1, then A is going to be smaller than B. So this same step we can continue here and find the final function. So I left it to you to find this function. So conclusion is this. This is a comparator circuit. This comparator circuit is an MSI element. So they sell this MSI element as 8 inputs and 3 outputs as an integrated circuit, one integrated circuit, MSI element. So all this design is inside this circuit. So you're not going to design this circuit. You're going to use this MSI element wherever you need to compare two numbers. Why I said to you what is inside the comparator, the reason is this. At the beginning of this course, to find the subtraction from the summation, we said we need to represent two numbers. If we don't use this representation, then in order to do the subtraction operation, you need to compare two numbers and give the sign of the highest number to the resulting number. So we said this requires a comparator circuit, which is this circuit. As you see, this is a difficult circuit. If you want to get rid of from that complex circuit, you've got to represent negative numbers as 2's complement form. In this case, your adder becomes your subtractor as well at the same time. That is the reason that I give you the details of the MSI element here.